Hello learners. Today we'll be discussing about greenhouse gas emission scenario. We know that the increasing average global temperatures, the rising of sea level and submerging of low-lying islands, the loss of biodiversity and shrinking of hotspots all over the world have led to increasing distress about the changing climates. Scientists all over the world are working on various strategies to understand the phenomenon of climate change, to gain an insight about its implications and also to quantify the changing climate by means of models. These climate models attempt to quantify the changing climate by using physical laws of radiation and energy and studying the radiation behavior and flux at the surface of the earth. In this regard, let us discuss about the greenhouse gas emission scenarios. Let us see the analog approach to understand the climate change. The analog approach is a novel method of testing the ground realities to the outputs of climate models. In this approach, the analogs tool connects the sites that are analogous or similar to climates at sites across other geographic locations, implying climates across space as well as time. This analog approach provides interesting observations on adaptation strategies to be followed for mitigating or at least minimizing the adverse effects of predicted climate change in future. The analog approach can help to relate global models, global climate models, with targeted field studies to explore the mechanism of adaptation. The analogs tool coupled with field studies link mathematical climate models with existing farm technologies in agriculture sector. The analog methodology can also use historical data to understand the case studies where the success or failure of adaptation mechanism can be identified. So let us see what exactly the meaning of climate models, what it constitutes. A climate model is a quantitative or qualitative representation of objects or a phenomenon. Computer models that simulate the Earth's climate are called as general circulation models. The climate models use physical parameters and physical processes as input to simulate the past climate and predict the future climatic conditions. These climate models represent mathematically the 5 components of climate system, namely the atmosphere, the hydrosphere, lithosphere, cryosphere and biosphere, based on physical and chemical principles of thermodynamics, fluid dynamics, radiative transfer and biological interactions. In recent years, inclusion of clouds and carbon cycle in climate models has also been emphasized. Thus, these models can be used to simulate changes in temperature, rainfall pattern, winds and oceanic circulations over a very long period of time. However, these climate models being based on certain assumptions and mathematical algorithms have certain limitations in simulating the Earth's climate, which is indeed very complex and is in dynamic state of flux. However, these climate models have improved greatly in the last few years to provide better insight into the future climate. The accuracy of these models can be tested by assessing their ability to simulate past and present climates. Having talked about the climate models, let us see different types of climate models. The first and foremost climate model is energy balance models. These energy balance models calculate the surface temperature as a variable for climate by considering the balance between the incoming solar energy and outgoing solar radiation in the form of heat released back to the space. The second model is the zero-dimensional model. These models consider the entire Earth as a whole unit, essentially as a single point. For example, a simple radiative transfer model that treats the Earth as a single point and averages outgoing energy. Next model is one-dimensional model. Besides treating Earth as a one unit, these models include the transfer of energy across different latitudes of the Earth's surface. The basic energy balance model equates solar energy absorbed by the Earth with the energy that Earth radiates back into space. Next type of model is the radiative convective models. These models are basically refinement of one-dimensional model, that they can determine the effects of varying concentration of greenhouse gases on emissivity and hence the surface temperature. Further, these models simulate the transfer of energy through the altitudes of the atmosphere by radiative transfer or convection for transport of heat. Radiative convective models can calculate the temperature and humidity of different layers of the atmosphere. Next type of model is the very important one, general circulation model, GCMs. These models are also called as global climate models and are four-dimensional models which simulate the climate based on physical laws, the flows of air and water in the atmosphere, and the ocean, as well as the transfer of heat. The different climate models project different values for rise in temperature for the next decade or for the next 50 to 100 years. This extreme gap between various climate models could be attributed to two basic factors. One is that the climate models are unable to factor in the effects of clouds. The second aspect is that the greenhouse gases concentration. We have access to the greenhouse gases concentration in the present time period, but we need to have the greenhouse gases concentration in the future. We need to have certain estimations, because how much anthropogenic influenced greenhouse gases are emitted into the atmosphere in near future, we should have a fair idea about it for running the climate models, because that is a key input to the climate models. Since such an impact of clouds and greenhouse gases would vary according to different human inputs, therefore scientists are the greenhouse gas emission scenario described in the SRES, that is Special Report on Emissions Scenario, four storylines or four main families like A1, A2, B1 and B2. And these families or the storylines reflect a particular trajectory of humanity and important hypotheses concerning demography, that is population growth, development, agriculture practices, technologies, etc. Or a set of scenarios that have been used in the IPCC 5th Assessment Report, AR5, for predicting future climate scenario based on climate models. Since these models were developed to represent possible future concentration of greenhouse gases emission by including a pathway that represents the trajectory of greenhouse gas emissions to reach a particular radiative forcing by 2100, hence the name representative concentration pathways. Radiative forcing, we have seen the concept of radiative forcing in the past sessions. Basically, it is a measure of the energy that is absorbed and retained in the atmosphere by greenhouse gases and aerosols. Thus, it can be either positive or negative, and it is basically affected by the concentration of greenhouse gases and aerosols. Changes in the land cover, that land dynamics, that is also very important, and also the total solar irradiance. Representative concentration pathways fix the emissions trajectory and resultant radiative forcing rather than the socio-economic circumstances. Thus, these RCPs can then be used to test policy decisions on mitigation and adaptation to climate change. There are basically four pathways based on the amount of radiative forcing produced by greenhouse gases till 2100. The first and foremost pathway is RCP 8.5. According to this pathway, the radiative forcing reaches greater than 8.5 watt per meter square by the year 2100. According to this pathway, the atmospheric carbon dioxide concentration in 2100 would be about 936 parts per million. The average temperature increase for 2081 and 2100 relative to the baseline scenario, that is 1850 to 1900 baseline, as per this model, that is RCP 8.5, is 4.3 degrees centigrade. While the likely range of temperature increase is between 3.2 to 5.4 degrees centigrade. In this pathway, the average global mean sea level rise for the period between 2081 and 2100 relative to the baseline 1986 to 2005 is 0.63 meter, while the probable range is 0.45 to 0.82 meters. This RCP 8.5, it is based on minimum efforts to reduce emissions. Let us see the second pathway, that is RCP 6. In this intermediate stabilization pathway, the radiative forcing is stabilized approximately at 6 watt per meter square after 2100. As per this pathway, the atmospheric carbon dioxide concentration in 2100 would be 670 parts per million. In this RCP 6 pathway, the average temperature increase for the period between 2081 and 2100 relative to the baseline, that is 1850 to 1900 baseline, as per this model is 2.8 degrees centigrade, while the likely range for temperature increases between 2 and 3.7 degrees centigrade. With regard to the sea level rise, the average global mean sea level rise for the period between 2081 and 2100 relative to the baseline, that is 1986 to 2005, is 0.48 meters, while the probable range is 0.33 to 0.63 meters. This RCP 6 pathway, it requires strong mitigation efforts with early participation from all the emitters, followed by active removal of atmospheric carbon dioxide. Means that sequestration of atmospheric carbon dioxide. The next pathway is RCP 4.5. In this intermediate stabilization pathway, the radiative forcing is stabilized at approximately 4.5 watt per meter square after 2100. In this pathway, the atmospheric carbon dioxide concentration in the year 2100 would be 538 parts per million. As per the RCP 4.5 pathway, the average temperature increase for the period between 2081 to 2100 relative to the baseline 1850 to 1900, as per this model RCP 4.5, is 2.4 degrees centigrade, while the likely range of temperature increase is 1.7 to 3.2 degrees centigrade. With regard to the sea level rise, the average global mean sea level rise for the period between 2081 to 2100 relative to 1986 to 2005 is 0.47 meters, while the probable range is 0.32 to 0.63 meters. The last pathway, that is RCP 2.6. In this pathway, the radiative forcing peaks at approximately 3 watt per meter square before 2100 and then it declines. As per the pathway RCP 2.6, the atmospheric carbon dioxide concentration, the average global mean sea level rise for the period between 2081 to 2100 relative to the baseline 1986 to 2005 is 0.4 meter, while the probable range is 0.26 to 0.55 meters. The RCP 2.6 aims to keep the global warming likely below 2 degrees centigrade above the pre-industrial temperatures. So to conclude, we have discussed about the role of climate models in predicting the future climate. Further, we have discussed the importance of climate analogs in climate change studies and greenhouse gas emission scenarios. Thank you.